Hello and welcome. I'm Pravir, and this session is integrating complex adaptive systems theory with whole systems quantum computing approaches. Now, in this session, we'll cover a brief overview of complex adaptive systems. I'll refer to this as CAS. We'll look at whole systems approach in quantum computing. I'll surface a quantum supremacy hypothesis that basically combines CAS with a whole systems approach. We'll briefly look at the landscape of quantum computing companies, focus specifically on D-Wave's approach that follows whole systems quantum computation. We look at some use cases broadly speaking, in the economic, social, environmental areas, using D-Wave's approach to quantum computation. We look at embedding CAS dynamics into Hamiltonians, and then finally, I'll conclude with ideas for further research and development. So beginning with an overview of CAS, here are some representative properties of CAS. There's complexity, and this arises from the large number of components and from the intricate network of connections and interactions between them. We have the property of adaptability, which is seen at both the individual agent level and the CAS as a whole. And this is based on changes in behavior in response to environmental changes or even changes from within a CAS. CAS also exhibits self-organization, and this generally leads to new structures or patterns that arise in response to real-time challenges. There's emergence, and this is to be distinguished from self-organization. It's a key property, and basically it cannot be predicted from understanding individual system components, but it arises due to the interaction and synergies between components. There's also nonlinearity, where small changes can lead to disproportionately large changes in output. And a couple of final properties I'd like to mention. One is being far from equilibrium, and this is a keynote of a healthy CAS to be distinguished from being in equilibrium. And then entropy, which can be thought of as a measure of the distance from equilibrium. And there's kind of like a Goldilocks zone or a sweet zone that you want entropy to be in so that CAS remain productive. Now, some examples of CAS are ecological systems, economic systems, social systems, biological systems. And the commonality here is that there's many different components that are generally independent, autonomous, and yet contribute to the CAS as a whole. When we look at whole systems approaches in quantum computing, there are some parameters or some properties that distinguish these. One is that of global quantum state manipulation. And this can be thought of as the entire quantum state generally being manipulated collectively rather than individually. So an example of this is that in the initialization of a whole systems quantum computing approach, generally all the qubits are put in a highly entangled or superposed state, and this becomes a starting point for computation. We have utilization of collective quantum phenomena, and these are examples of entanglement amongst qubits that enable complex interconnected computations. There's superposition that explores multiple possibilities simultaneously. Then we have this feature of encoding a problem in system dynamics. And this is where the problem is directly encoded into the physical properties of the quantum system. And then in using the example of quantum annealing, a solution to that problem is generally found by guiding the system towards its lowest energy state, but it's a whole system as opposed to individual qubits. We also have, as examples of whole systems approaches, that of adiabatic evolution and measurement-based processing. So adiabatic evolution is where the quantum system as a whole there's an attempt to maintain it at a ground state so that when the computation is complete, then the end state reflects a global optimization state. We have the idea of measurement-based quantum computation that starts with putting all qubits in a highly entangled state to represent all possibilities, and then subsequent measurements generally change the quantum state at a global level and steers the computation towards the final result. We also have this inherent idea of scalability and error robustness, because as opposed to a gate-based approach, the idea here is that it's easier to add additional qubits, but since you're operating at the level of all qubits, there's scalability becomes easier, and robustness against errors also is easier. Now, let's get to the quantum supremacy hypothesis. And this basically is stating that quantum computation approaches that leverage whole systems computation should correspondingly be closer to exhibiting quantum supremacy. So let's look at this in a little more detail. So we know that in all quantum systems, whether they're gate-based or whether they're whole systems-based, there's a degree of nonlinearity, interconnectivity, and that's just the nature of quantum phenomena. But what's being suggested here in this quantum supremacy hypothesis is that because a whole systems computation is involving many qubits or all qubits simultaneously, there's a threshold level that is crossed by which some of the CAS principles that we had been introduced to earlier operate more abundantly. And as we know from study of CAS systems in general, when we approach a problem from a CAS point of view, it yields better results than if we approach it from a linear point of view. And so that hypothesis is carried into the quantum realm. Again, the key distinguishing point being that if the quantum system can operate beyond a certain threshold where many of the qubits are simultaneously exhibiting these CAS properties, then the likelihood of displaying supremacy is going to be higher. So I'm not going to spend a lot of time on this, but if we look at nonlinearity and interconnectivity, then as we know, CAS are defined by nonlinear interactions where small inputs can lead to large and unpredictable outputs. Similarly, quantum systems inherently exhibit nonlinearity due to phenomena of quantum interference and entanglement. Further, quantum tunneling is utilized to overcome energy barriers. So there can be disproportionately large effects in getting away from local minima in the energy landscape. Entanglement leads to profound levels of interconnectivity amongst qubits. And so we're seeing that this nonlinearity and interconnectivity that we know is a CAS property also can exist in abundance in certain quantum approaches. When we look at another CAS property of adaptation and evolution, then similarly in whole systems quantum computation, we see that the system evolves towards a minimum energy state and it adapts its configuration to find an optimal solution. And again, the question is it crossing a threshold so that that CAS principle is operating globally. When we look at emergence, then in quantum computation, solutions to optimization problems emerge from the computation. And just as in CAS systems, these are not predictable, are not always predictable from individual behaviors of qubits alone, but it's the combination of quantum mechanical properties. And in this approach that's being suggested here, those quantum mechanical properties being beyond a certain threshold simultaneously. Similarly, scalability and robustness, we know that these are CAS properties in that adding more components to a CAS, so long as it's operating as a CAS, will maintain its ability to scale and also robustness in operations. So when we look at whole systems approaches in quantum computing, we also maintain coherent quantum states across an increasing number of qubits to thereby also make scalability easier, as was suggested earlier. Now, when we look at the landscape of quantum computing companies, then we have, in terms of approaches, we have annealing quantum computing, we have a gate-based approach, we have another gate-based approach, but I break it out as a topological approach to quantum computing. And then we have the measurement-based quantum computing that I had mentioned earlier. And when we look at companies that basically follow these, we have D-Wave as an example of annealing quantum computing, IBM and Google, Rigetti Quantinuum as gate-based approaches, Microsoft as topological, but is still also gate-based approach, and then Xanadu as a whole systems approach to quantum computing, but specifically the measurement-based quantum computing approach. Now, the question is, how is entropy managed in each of these different approaches? And again, the hypothesis being that if entropy is managed in such a way that it becomes the lowest possible, then the likelihood of quantum supremacy arising is going to be higher. When we look at annealing quantum computing, the system starts in a very high entropy state because all the qubits are put into a superposed state, which is a state of maximum uncertainty, but it's gradually and adiabatically moved towards low entropy, and that final state contains a solution. There have been several instances that have yet to be peer-reviewed, but in March 2024 example, there was a paper submitted demonstrating computational supremacy in quantum simulation of non-equilibrium magnetic spin dynamics. And there have been a couple of other instances of supposed quantum supremacy even before this. When we look at gate-based approaches, the way that entropy is managed here is that the idea is that you've got quantum algorithms, and these are executed through a series of quantum gates that manipulate qubits. And each gate application modifies the state of the qubits. So initially, the qubits are in a known state. It's a low entropy starting point. As the algorithm proceeds, it goes to higher entropy, and then again, it reduces to a lower entropy. And there have been some controversies around supremacy. These were indications of supremacy as early as 2019. So there's also been more time to disprove them, but where Google had claimed quantum supremacy, solving a problem in 200 seconds that they said would take 10,000 years, IBM refuted that, saying that they could solve that problem in a few days using a supercomputer. Topological quantum computing basically uses anneals, which are quasi-particles that exist in two-dimensional space, and braiding, that's a process of moving one anion around another. And this approach seeks to leverage properties of anion-based topological qubits that are inherently error-resistant because they're deeply connected to the 2D space they inhabit. And this is in contrast to, say, qubits used in a gate-based approach that would, in comparison, be much more disconnected from the environment in which they exist. So potentially, this is still a theoretical concept as far as I know, but here also entropy is moving from more to less as the computation proceeds, but it's too early to say anything about it. Then you've got measurement-based quantum computing, and here you've got Xanadu that uses photonic quantum computing. And measurement-based quantum computation is known as a one-way quantum computer. So it starts with a cluster state, which is a highly entangled resource state. And then computation is performed entirely by measurements. So each time a measurement occurs, then you get from all the possibilities of a solution toward a single solution. And so again, here entropy is reduced through the process. And in 2022, Xanadu claimed that its computer Borealis performed a task, specifically Gaussian boson sampling, that would take a classical computer thousands of years to complete. Now, because D-Wave has been on the market the longest, its commercial applications have been around for about 15 years or so. I want to focus on its approach. And we can think about the initialization of its quantum annealing process. And this is represented by the initial Hamiltonian, in which a strong transverse magnetic field basically allows the poly X gate or poly X state to occur across all the qubits in that computer so that they're put into a maximum state of uncertainty. So they're all superposed simultaneously. And that's represented by being both in the 0 and 1 state simultaneously. And what that signifies is that if there are n qubits in that quantum computer, then there's 2n possible states that are all being superposed. So all possible solutions are being represented in that in the initialization of the quantum annealing process. There's a process of encoding the solution, the problem to be solved in the quantum computer. And we can think of I and j as being different qubits that represent different variables. And we can think of the big J and the H as being constraints that exist in that problem. So you've got variables and you've got constraints, and then this is all encoded in the qubits and the interaction of the qubits. And basically, there's an adiabatic evolution towards the solution. So it starts from the initial Hamiltonian, and that's represented by HI here, and you get toward the final Hamiltonian, but it takes place through a scheduling function where AT decreases and BT increases as the process evolves. So this all has to be maintained at a ground state so that the final state in which the computer ends up represents the optimized solution. Now, to make that more concrete, let's look at a use case. So here, this is an ecosystem services. And imagine that here we have a Hamiltonian to basically has to do with maximizing biodiversity. And a specific objective could be maximize the number of species sustained in an area while managing resource use. So over here in this Hamiltonian, if we think of I as being the habitat suitable for a species I, then Ni is basically the presence or absence of that habitat that's suitable for species I. Ai is a coefficient that represents the benefit of maintaining the habitat for species I. And then when we think of the habitats for two species, I and j, and the connection between them, then Bij can be thought of as representing the benefit or the cost of having both those habitats together. And so this is then suggests you can look at a large number of species, a number of different habitats, and the connection between them, and that's how the problem is encoded in using this Hamiltonian, but then through that adiabatic evolution and the scheduling function, it evolves towards some idealized state. Similarly, we can have economic problems that are represented in the same format and social problems that are represented in the same state or in the same way. And here I want to suggest embedding CAS dynamics. So while we have the same scheduling function, ATHI plus BTHP, which represents the final Hamiltonian, through envisioning CAS dynamics, we can create some other kinds of Hamiltonians. And here I'll just focus on a particular Hamiltonian. But before I get into it, let me just step back into CAS theory. Generally, in CAS theory, as I shared in the beginning, there's many different CAS properties, but there's some foundational properties. For example, interconnectivity, feedback loops, distributed control, self-organization. If these exist in CAS, then we can expect the CAS that's displaying these properties to also begin to display more sophisticated phenomena that we want to see in CAS, such as coevolution, diversity, adaptiveness, emergence. And we want CAS to get to that. But in order to get to that, there needs to be some initial CAS dynamics in play. And so if we try to represent this feedback explicitly, we already know that's happening within a quantum system, but here we're just trying to call it out and then amplify it through embedding it into the algorithm itself. And if we think of this feedback being such that you've got a control coefficient, CIT, which basically affects the feedback applied to component I at time t, and the feedback function itself is represented by GTX, which basically represents the feedback on the system state X at time t, then this gives us the overall feedback that's happening in the system. So if now we create some kind of intermediate Hamiltonian that, say, has this feedback Hamiltonian embedded in it, amongst other CAS dynamics, then we can create a scheduling function such that we've got AT decreasing as the system evolves, BT increasing as the system evolves, and then CT being some kind of other function in which that feedback is amplified. And so what happens here is that you've now got a new scheduling function that incorporates CAS dynamics in it. In effect, you've incorporated a more complex algorithm that has CAS dynamics in it now. So some ideas for further research and development. There's, first of all, advanced Hamiltonian and quantum algorithm design, leveraging off the point that I just made. So based on deeper CAS theory and alteration of the scheduling function, it should be possible to develop even more sophisticated Hamiltonians that are fine-tuned to the problem that we're trying to solve at a particular time. Now, the advanced Hamiltonians may also be created based on new mathematical models that effectively encode complex multivariable interdependencies that leverage other CAS properties, which we haven't looked at in this presentation, such as strange attractors, fractals. We touched on far from equilibrium, amongst others, but these can also be embedded into Hamiltonians. Another idea for further research and development is to validate and augment CAS theory using whole systems quantum computation. So CAS is a theory in development, and we can validate theoretical CAS models through empirical research implemented and tested on actual quantum hardware like D-Wave. So by embedding these algorithms that now contain different CAS dynamics into the hardware, the validation and augmentation of CAS theory can take place in this way. So this suggests using whole systems quantum computation to, in fact, augment CAS problems and perhaps even CAS theory. Another idea for further development is systematizing the approach to repeatable quantum supremacy. So augmenting CAS theory and being able to create advanced Hamiltonians and quantum algorithms sets up a virtuous cycle. So research, stepping back, research into the most effective CAS-based levers and the best ways to embed these in whole systems quantum systems will provide insight into systematizing the surfacing of quantum supremacy. There's also the opportunity to integrate, or the integration of machine learning with CAS and quantum computing. Here we combine machine learning techniques with CAS principles and whole systems quantum computing to create hybrid models that can then learn and adapt from data generated by whole systems quantum computation dynamically. And then finally, what we can do is we can also develop quantum-enabled CAS simulation tools. So create specialized software tools that facilitate simulation and analysis of CAS using whole systems quantum computation. And these tools would allow researchers and practitioners to model complex systems, run simulations, analyze outcomes by leveraging whole systems quantum computational resources. And finally, this suggests also interdisciplinary collaboration between quantum physicists, complex systems, theorists, practitioners, economists, ecologists, computational scientists, and so on. Thank you.